Okay, thank you everyone for rejoining us. And we have Antoine from CERBAIR in the chat here. And Antoine, do you want to give us a hello? Check the mic is working.
Sure. Hello. Is everything okay? Is everything working?
Sounds perfect. So after this, you'll get to share your slides and take it away. So thank you for joining us, and I'll let you continue with your presentation.
Thank you very much, Mike. Hello everyone. My name is Antoine Menini, and I'm the CTO of CERBAIR. CERBAIR is a French company that is specialized in providing counter-drone system. The company was created in 2015. We develop, manufacture, and sell our own counter-drone solution based on radio frequency detection, and we work with major French and international government institutions. Today, I'm going to talk to you about the miniaturization of drones and its impact on radar versus RF detection. We are going hopefully to debunk some common myths about drone detection, and I'll try to show you why RF detection still remains a good choice when it comes to detecting drones. Oh. Sorry. So first, let's have a look at the biggest drone manufacturer in the world, which is DJI. You will see in this slide the evolution of their consumer drones from the first DJI Phantom that was in 2013 to the latest DJI Mavic Mini 2 that was released just last year. Also, it was a bestseller. DJI has now abandoned the Phantom series to focus on the Mavic series, whose drones are way smaller and easier to carry around than the Phantom ones. You see, for instance, that the DJI Phantom, the first one weighed 1,200 grams, while the weight of the latest Mavic Mini 2 is only 249 grams. And we see the same patterns with other big drone manufacturers, such as Parrot, with their Anafi drone, for instance, which is also a very small drone. And we'll try to have a look now at what makes this evolution possible. So drones are becoming more and more intelligent with more sensors, more features, better cameras. At the same time, they are becoming smaller. So this change is mostly driven by the smartphone industry. The race to better smartphone cameras and more processing powers has allowed electronic manufacturers to get better components that are at the same time also cheaper. Let's take, for example, the ARM CPU architecture. If you have a smartphone, most likely it will use this kind of processor rather than the x86 Intel architecture used by a computer. The advantages of this architecture is that it consumes less power, therefore produces less heat, while at the same time being small in size. Apple has even decided to make a computer with this exact architecture. This is the Apple M1, which is used in the latest MacBook. So the ARM architecture is really great for low power consumption, and this improvement in low power CPU are now used in drones to allow them to have more processing power. Cameras have also improved a lot in the last year. So you might have noticed that current generation of smartphones now have 2, 3 more cameras that have high resolution, and the same sensors that are used in smartphone can be used in drones to get awesome pictures. If we compare, for instance, the size of the camera of a DJI Phantom with the latest cameras of the Mavics, we see that the size has decreased a lot, and at the same time, the resolution and the quality has increased. So this major pushes on the smartphone industry also benefits the drone industry. Batteries represent almost a third of a drone's weight. Battery technology has also faced a strong evolution. First, also because of the smartphone industry. Now the batteries on the smartphone are getting better and better every year. but also more recently, thanks to the research on electric vehicles and electric cars. This means that nowadays the battery can deliver the same amount of energy and are lighter than before, which lead to smaller motors in drones, smaller propellers, and in the end, increased autonomy. So some studies suggest that the battery energy density, so this is a ratio of energy per unit of weight in a battery, has tripled since 2010. This means that we are now able to put 3 times more energy in the same battery than we were able 10 years ago. And the drones that we see now, the DJI Mavic Airs, for instance, were technologically not able to exist 10 years ago. The way we use drones has also changed a lot. So 10 years ago, drone couldn't do a lot except for maybe flying a little bit, not far away, not a very long range. The battery didn't last as long as today, and flying a drone was more than a hobby. Most of us remember the first drones that were really big and that you had to carry around in a big backpack. This has changed a lot. Now drones are smaller, more affordable, and capable of a lot of things, and people view them more like a tool to take great pictures or video while doing other stuff. For instance, now when you are doing sports like skiing or running, the drones are automatically able to follow you outdoors and to take great pictures of you. So they are now viewed as a companion in leisure rather than a leisure themselves. And therefore, they have to be able to be packed in a suitcase very easily. This was not the case in the first generation of drones. Regulation is also a major incentive for drone manufacturers to come up with drones that are under some weight limit, so that users of drones will get less restrictions. A good example of this is the new drone regulation that was just passed in the European Union. As you see in the table, the regulation organizes drones into different categories, C0, C1, C2, C3, and these categories are based on their weight. So you see that the law is not the same for all types of drones, and drones under 250 grams require no training at all and can even be exempt for registration if they are considered as a toy. So I'm sure that now you might probably understand why the new Mavic Mini 2 weighs exactly 249 grams, so that users are able to use it almost freely without being able to have any regulation difficulties. So all of this pushes for drones that are smaller, but now let's have a look at the consequences on radar detection that these smaller drones have. So first of all, what is radar detection and how does a radar work? Radar is a tool that detects physical objects. Basically what it does is that it sends an electromagnetic wave at a very specific frequency. This wave is then reflected on the object, that's called the echo, and the echo is used to determine the direction and the distance of the reflecting object. If the object is moving, the frequency will slightly shift on the echo, and this is called the Doppler effect. So we can use this effect to get the speeds of the object relative to the radar. Radar is a great technology that has been used since World War II as the primary way to detect airplanes all around the world. So it's really a great tool, but it's kind of difficult to use in drone detection. The first problem with radar when dealing with drones is the range. In order to be able to properly analyze the return signal, this signal, of course, has to be strong enough. The proportion of the reflected signal on an object is called the radar cross-section, or the RCS. Radar cross-section depends on many factors. First of all, for instance, the material of which the target is made, the size of the target relative to the wavelengths of the radar signal. So this is the frequency. But one of the most important is the size of the target. And so as drones are becoming smaller and smaller, they are made out of plastics, then the RCS, the radar cross-section of the drones, is also becoming smaller, and it's really difficult to detect them at long range. So we need more and more powerful radars to detect these types of drones. Radar also will detect everything. As we see, they send a wave, the wave is reflected, and everything will reflect the wave. So we need a treatment, we need to apply a treatment to eliminate what is called the ground clutter. Clutter basically is the reflection on everything with the radar. So the wave will be reflected by the ground, by buildings, by trees, by almost anything. So the first process that is being used is called moving target indication, or MTI. This process is based on the speed of the object that is detected. And we want to eliminate stationary objects to be able to filter out the clutter. The problem with drones, compared to airplanes, for instance, is that they can move very slowly. Or they can even stay stationary. So it's very difficult to find a good threshold. If the threshold, for instance, is too low, you will detect everything. You will detect the ground. You will detect the buildings. You will detect everything. But if the threshold is too high, you will not detect drones that are moving slowly or that are stationary. So engineers have come up with new solutions to face this issue. So also the process is not perfect because there are other moving objects that we want to eliminate, like branches or trees or people walking or cars. So engineers have come up with a new solution and a new way of discriminating target. This way is called a stationary target indication, or STI. Here, the idea is to exploit some intrinsic characteristic of the moving object, like, for instance, the apparent size, which is relatively small compared to ground clutter. So, for instance, the building will reflect a lot of energy, whereas drones or smaller objects like that will reflect smaller energy. We will be at a different distance. So this is used a lot to do discrimination of targets. But the problem is that there are other targets that we would like to discriminate, like birds, for instance. Birds causes a lot of problems with radars because their size is approximately the same as drones. And so the radar cross-section of birds is approximately the same. Birds, as you know, are made mostly out of water, and water reflects radar signals a lot. So we need a way to discriminate birds against drones. So most of the times, this way is the micro-Doppler effect. So we already saw in the previous slide the Doppler effect, which shifts the frequency of the return signal if the detected object is moving. So now, if the detected object or any structure on the detected object has mechanical vibration or rotation, it will induce a frequency modulation on the return signal. This frequency modulation can be detected, and this way we can see what type of object we are detecting. And so this is typically the case of the drone's propellers, which are rotating when the drone is flying. And this is a great way to discriminate drones against birds because they have a different microdoppler signature. However, you have to understand that this effect strongly depends on the size of the moving object and of the material of which they are made. So drones are becoming smaller, so their propellers are becoming smaller. So it's becoming more and more difficult to detect them using microdoppler effect because the propellers are now made out of plastic. They are not made out of metal anymore. And the effect of the microdoppler is also stronger on quadcopters than on fixed-wing drones, because fixed-wing drones have generally only one propeller. And finally, it's important to understand that the detection of the microdoppler effect is only possible at a distance range shorter than the standard detection distance. So if the range of the radar gets lower, then the range of the microdoppler detection gets also lower. For instance, so if we take quadcopter drones and a radar that has a detection range of about 1 kilometer, for instance, then the range at which we'll be able to detect the microdoppler effect will be something like 500 meters. So as drones are becoming smaller and smaller, it's really difficult for radars to be able to detect them because of the physics of the radars and of the physics of the waves. So in conclusion, we see that drones are getting smaller thanks to new available technology, mostly available technology made of consumer smartphone markets. But obviously, the strength has also some limits. So for instance, smaller drones will have more difficulties to fly during high wind. And so the smallest of the drones, you see sometimes nano drones that are like 10 centimeters wide. These nano drones are really difficult to fly outside because of the wind. Also, in order to be effective, the communication antennas of a drone need to have a certain size. So typically, for instance, at 2.4 gigahertz, the typical size of an antenna to work properly is 6 centimeters. So if we want to lower the size of the drone, we'll need at some point to decrease the size of the antenna, and this will not be great for propagation. Also, batteries are getting more effective, but as we saw, battery only represent a certain percentage of the drone total weight. We saw that on DJI drones, battery represent approximately a third of the drone's total weight. So even if battery technology will most likely continue to improve in the future, thanks to smartphones, thanks to electric cars, we'll still need other parts on the drone. We'll still need motors, we'll still need propellers and other components that are more difficult to miniaturize. So that means that the effect that miniaturized drones also have some physical limits. But as a matter of fact, they are still continue to becoming smaller and smaller, and it's more difficult for radar to detect them at reasonable range because, again, of the physics. For instance, you can see this nano military drone on the right of the screen. This drone is called the Black Hornet. So even if the flight capabilities are not the same, of course, as the one of bigger drones, this drone is almost impossible to detect using radar technology. So this is where other complementary technology can be used to detect drone, and one of them is passive RF technology. So let's have a look at what passive RF technology is. Most of the time, when you use a drone, there is a bidirectional communication between the drone and the pilot in order to fulfill a mission. So the pilot with the remote control will send command to the drone, and the drone will send back the telemetry data. So real-time position, speed, sensor status. But most importantly, the drone will also send the real-time video link. The pilot most of the time is able to see in real time what the drone is doing, what the drone is filming. So the principle of passive RF system is to detect this two-way communication. Most of the time, this kind of system relies on the drone signals database and is able to detect both the drone and the pilot. So one of the great things about this type of system is that it does not depend at all on the physical size of the drone. A nano drone, a small drone, can be detected as easily as a big drone that is 10 meters wide, provided, of course, that the signal power is the same on both drones. Also, contrary to radars, it does not need any direct line of sight between the drone and the detector. So RF detection is a great technology that is very complementary to radars. But many people argue that today, with the state of technology in artificial intelligence, we can have drones that are fully autonomous and that have no data link at all. Drone can be programmed using GPS waypoints or even image recognition algorithms to perform their mission without being controlled from the ground. So for such drones, of course, passive RF detection is simply not possible as it relies on radio frequency communication between the drone and the pilot. So if there is no communication, if there is no radio frequency whatsoever, we cannot detect it, of course. So such technology exists a little bit, but we'll see that it's far from perfect, does not work, it's not magic, and also it's operationally quite difficult to use. So we'll see some examples of this. So why is it difficult to have drones that are fully autonomous? It's because communication when using drones is essential. So communication takes a vital part in a drone's missions, whether they are civilian, military, benevolent drone, malicious drones. Communication is really important. So let's imagine, for instance, that you have a reconnaissance mission and you want to explore the site to obtain some information about enemy presence, activity. Of course, it's a good idea to send a drone because you will reduce the risk on the operators. You send a drone first, and then maybe you do something else. The thing is that you don't necessarily know in advance what you will look for and where you will need to look. You can imagine, of course, filming with the drone without any transmission. So you store the data on the drone performs its pre-programmed mission, and then when the drone comes back, you can retrieve the data and see everything that the drone has filmed. But what it means is that the information that we'll get from this could be outdated. During the 10 minutes of the mission, things could change, people can move. And also you risk losing the drone, because if you lose the drone, if the drone is shot, if the drone has a technical problem or anything, you will get no information at all from this. So we see that live information for reconnaissance is really key. That's why most of the time, even if the drone is pre-programmed, the operators want to get the live video of the drone to be able to see what's important and to be able to change the mission. So imagine now that you want to use a drone to destroy a target, for instance. So drones are used a lot for target designation because they are quite precise, and also because we reduce the risk as well for the operators. but drones are also used directly as a mean of attack. So obviously, you can program a drone. Obviously, you can program a drone using GPS waypoints, and you can program it to attack a precise position based on the geographical coordinates of the position. But there are some drawbacks that you must take into account. So first of all, the position of the drone using GPS will most probably be inaccurate by a few meters. It's not a lot because GPS signals are quite accurate, but this could cause you to miss the target, especially considering that most of the time drone payloads are limited, so precision in hitting the target is a key. So programmed drones are not very good to attack target. Second, if you do this, you will rely solely on GNSS satellite signals, and this GNSS satellite signal can be spoofed or jammed, and this could destroy the mission. Also, the target has to be stationary, so you cannot use GPS waypoints to attack a convoy, to attack a moving person. So we see here that with these two small examples, even if technologically we can program a drone to perform some missions, operationally, it's a little bit more difficult than that. It's not as easy as just pressing two buttons, saying, okay, I select this target, attack this target. Unfortunately, communication between the drone and the operator is still essential. Then we'll see that identification is also essential. So you might know that drone regulation all around the world is pushing for drone remote identification. So if I take the example of France, for instance, that I know quite well, France has passed a law that requires drones over 800 grams to constantly send in the air their identification number as well as their live position. The EU and the US are working on quite a similar regulation, and this will allow authorities to control drones way more easily. But this type of system is also very important for military drones, even if the purpose for military drones is a little bit different. It's very important, operationally speaking, to be able to recognize your own drones when you are flying them to avoid unintentional friendly fire. For a long time, as you might know, airplanes have been equipped with IFF system, identification friends of foe, which uses radio transponder to identify the broadcaster. This is really important because as more and more airplanes are flying, if you don't have a clear situation, especially during war, you can have issues. In 2003, for example, during the Second Gulf War in Iraq, a British Tornado was shot by American Patriot missile, so friendly shot, because of technical deficiencies with the IFF system. So we see that it's very important to be able to communicate with your drone, but also to be able to identify your drones. So, as a conclusion, there are, of course, a lot of trends in artificial intelligence and autonomy. We see it for autonomous vehicle, and we see it, of course, with drones. But we see that drones rely a lot on communication to perform the mission. So most probably, they will continue to use RF data link and to be detectable by passive RF system. At the same time, the technology allows for these drones to be smaller and smaller while performing the same mission. So of course, radar technology is great and will continue to stay a primary way to detect moving objects like drones. But we see that there are some drawbacks and that radars face a lot of difficulties when dealing with drones, especially if the drones are smaller and smaller. Sure, it's a little bit easier to detect a big Reaper, a big military drone using radar, but for nano drones, as the one that we have seen before, it's much more difficult. And this is where passive RF technology, I think, will always be a great complementary choice. And of course, the best solution is to have the two of them working together. So this is the end of my presentation. Thank you very much for listening to me, and I'm happy to answer any question that you might have on the internet.
Brilliant. Thank you very much for the presentation, Antoine. And I know we do have a few questions. So starting off, and it was quite interesting, I must say, on the RF silence side, we've got something on that. But the first question I want to ask you was, what is the difference between, mainly focusing your detection on, say, smaller systems versus some of the larger drones that can carry heavier payloads?
Well, it depends strongly on the threats that you have and what you want to detect. So, for example, if you are a military, you might want to detect bigger drones that have higher payload because the threat that you face is basically bombing, and the opponents that you have, they will use bigger drones. If you want to protect a sensitive site, the biggest threat that you might have is spying. And spying, as we have seen, can be done using small drones like the DJI Mavic Mini, for instance, which are like consumer drones that are all available and not expensive at all, but they can even use smallest Black Hornet drones. So I would say that it strongly depends on what problem you are facing and what you want to protect against.
Okay, yeah, brilliant. And the next question touches on the previous speaker who was talking about the cellular networks that are controlling drones from, say, a drone operation control center. So with some of those cellular networks starting to interact or control drones autonomously, will RF detection systems still be relevant in these scenarios?
So, of course, cellular networks poses major threat to RF detection. RF detection relies on drone signatures, and if drone use 4G networks or 5G networks, the signature will not be any different than with a smartphone. So it causes issue with RF technology. Of course, there are solutions to this. But I don't think that all of drones will start using 5G in the next few years because it's really complicated. Basically, drone 4G has been available for a long time now, and drone can be controlled by 4G. But even with this, you see that there are not a lot of consumer drones that use it. Because of the complexity and because you rely on something else. Whereas if you have your own drones with its own communication, you rely only on your communication. So it's a little bit easier to handle, especially in war scenes. It's easier to have your own communication than to rely on 4G, which is not reliable at all and can be jammed.
Okay. Yeah, very interesting. And I think, technology will catch up to that point when that is happening. And a lot of the malicious, pilots will probably not choose to go along those lines of remote ID or interconnected systems just yet. So, okay,
exactly.
interesting.
And you have to consider also that if you use 5G communication, it's easier to trace you because you will need a SIM card. You will need to be registered on a certain network. So of course, it's a little bit more difficult to detect. But at the same time, if you are malicious and you use cellular communication, it's easier to trace you. So that's one of the drawbacks.
Okay, very interesting. So the next question, Antoine, was how will RF detector systems fare when it comes to small, fast-moving drone swarms or multiple drones at the same time?
So that's a really good question. Drones. Nowadays, you can have a lot of drones using the same frequencies. Of course, drones are made and signals are made to be used at the same time. So if you see smartphones or Wi-Fi, you can have a lot of Wi-Fi discussing at the same time, a lot of Wi-Fi device and lots of smartphones. And it's kind of the same with drones. Also, drones have to send a lot of data because most of the time they send a huge video file which with high quality, but you could imagine having 10, 15, 20 drones flying at the same time. Of course, it poses issues to RF detection because, again, it's a little bit more difficult to detect when there are a lot of them flying on the same frequency range. But we've seen, and we have seen this with our system, that if the drones are able to communicate together without a lot of interferences, we are also able to detect them without much issues. And the same thing the same difficulties will happen to radars. When there are a lot of tracks on the radar, it's a little bit more difficult to detect.
Okay, no, it makes sense. And a question from me on the back of that is, if you have an RF link that is being established when the drone is on the ground and the pilot is turning it on, versus a drone that was turned on a lot further away and comes into range, will you detect, or will the systems with RF detect that drone initially starting up when it's on the ground, or does it fare better? Yeah, go ahead.
Yes, so if it's on the range, we're able to detect the drone and the pilot, even if the drone is not flying yet. So this is one of the great things with RF detection. If you want to start a drone not far away from the system, as soon as you start the drone and as soon as the drone and the pilot start communicating together, both will be detected. So if you have jamming, for instance, you could start the jammers, and the drone will not be able to take off, basically.
Okay, very interesting. Now, there's another question here that I'm going to continue down the RF space with, and it says, what about RF in in RF heavy environments? Sometimes we see testing conducted in aerodromes rather than a city where there's lots of critical infrastructure. I think they're trying to say in cities where there's RF heavy environments or places like critical infrastructure with probably unique or nuanced RF signatures.
Yes, of course. So this is also one of the drawbacks with RF is that it depends a lot on the environment. So if you have an RF heavy environment, as you said, it's way more difficult to detect. So you will lose some range, obviously, and you will not be able to detect the drones a few kilometers away, as you will do in non-urban environment. But the thing is that at some point the drone will need to communicate with the pilot, and so in RF heavy environment, most of the time you will see that the pilot will also lose range on the drone. So the pilot will need to be closer to the drone in order to be able to fly it. So the drone will come from closer, you will be able to detect it. So of course, it causes issues on the RF system, but the same issues are caused to the drone and to the pilot of the drone. And so one of the forces of the CERBAIR system that we are developing is that we try to filter and to eliminate all this noise to be able to detect only what's relevant inside of it.
Okay, and just out of interest, when you are, say, testing your detection systems, would that testing take place in replicas of real life environments, or is it always usually done in, say, a Faraday cage or a closed environment or an open field? What's your testing journey been like in terms of trying to get that right and measure out those filters?
Yes, so of course, most of the time we test our system in open field, but we also like to test our systems in real life environment a lot. So for this, of course, we have installation on customer sites from which we're able to get a lot of feedback. But also we like to move our system. So last week I was right at the center of Paris. You can imagine that there are lots of Wi-Fi networks, a lot of cellular networks in the center of Paris. So the RF environment is quite horrible. but we like to test our system in this type of environment and to get some data to continuously improve our algorithms.
Okay. Talking about your own algorithms might be an interesting intro for this question here. It says, if innovation in drones is being driven by smartphones and batteries, what is driving best of class RF detection in terms of innovation, or what is RF gold standard?
That's a good question. So I think that the best-in-class RF system is driven by simply by the counter drone industry. We see that for like 5 years, when CERBAIR began working on this project, there were like 3, 4, 5 companies that were doing counter UAV systems. And now there are more than 300 companies in the world that are doing it. So there are top-notch engineers that are working all over the world to find out a solution to detect drones, because it's really difficult to detect them using RF technology, using radar. The technology is quite difficult to master, but at the same time, there is a lot of demand to be able to detect drones and to be able to protect against malicious drones. It could be on airports, it could be on stadiums, prisons, cities, military sites. So there are lots of sites that have threats because of drones. So I think that demand is what is pushing the market.
Okay, brilliant. And there's a question as well that said, have you ever tried to detect the Black Hornet drones, as you showed in the end of your presentation?
So this is a military drone. So CERBAIR does not focus itself on military drone. Also, we sell our solutions to military people, but our goal is to detect commercially available drones. So Black Hornet is not one of the commercially available drones. So it's not what we focus on, so I could not discuss it further.
Okay, that's a good answer. And I guess at the same time, if you think about, say, Parrot, even that it comes out with commercial or enterprise, and then drones that are used within blue SUAS or kind of military standard, where does your bar kind of sit in terms of those are the ones we'll focus on to detect versus those ones we'll leave out?
So this is a difficult question, but of course, so that's why the goal of CERBAIR is to detect commercially available drones, because if the drones is commercially available, everyone could use it and everyone could use it maliciously. If the drone is specialized for any forces or stuff like that, then it's a gray area for us, and we don't want to detect it because it could also cause some issues for our users. So the red line for us is we detect drones that are commercially and freely available on the market, and we don't try to detect drones that are not. So that does not mean that we are not able to detect them, but we don't focus on them.
Yeah, brilliant. Okay. And I've got another one here from that came in from Twitter. It said, some countries allow the demodulation and decoding of RF signals, as in it's illegal in terms of law. How could you advise when it comes to detection? Are you banned from detection in any countries?
Not that I know of. So you have to know that we don't do any signal demodulation. So we are able to detect the packet. So we know that there is a communication between the drone and the pilot, but we don't know what this communication is. So this is a big difference between our type of system and other types of system that do basically like signal listening and signal demodulation, and that are a little bit more difficult to use because of the regulation. From my knowledge, there are no limits to the use of detection, passive RF detection system, because they are listening to signal that is everywhere, but they are not trying to understand what the signal is telling.
Okay, brilliant. And we might go for one last one, unless any more come in. And that is, what is the difference between having many small hardware RF detection systems versus one large RF detection system at, say, around an airport?
So it's a big question. It's a good question. So first, you have to understand that there's a big difference between radars and RF for this topic. So radars, the range of a radar depends on the radar itself. So it depends on the strength of the signal that is being sent by the radar. So there are radars that can detect drones at more than 10 kilometers, even if, as we saw, it's very difficult. But there are radars that are very short range and that can detect drones up to 500 meters, 200, 100 meters. For passive RF system, it's a little bit different because our range depends on the signal that is emitted by the drone. So it's not like you can build a system that has a very short range and then another system that has really long range. Of course, there are things that you can do, but most of the time, all the stuff depends mostly on your algorithm, the quality of your material. So you could, for instance, for airport, if you want to protect an airport, you will need to put several RF system at several sites, several points on the airport, because airports are very big sites. So one system only would not be able to detect drones flying all over an airport. So this is one of the reasons why you want to put multiple systems. Another reason would be to prevent from communication. So some of the times it's really difficult to find a good spot to put one RF system, because the good spots are already taken by cellular mobile antennas. So this way, maybe you want to put multiple systems at multiple sites, so that you can take advantage of this and have less interferences.
So if you don't mind, I just want to dig into that. If you were going to a site and you were looking for the perfect place to put your RF detection sensor, what would your thought process be, and what would be the most ideal site to place that for the greatest coverage and range?
So when we do this, we do what we call the site survey. So we have engineers coming to the site, and they are trying to determine what is the best position to put the system. So of course, RF system needs to be put high in the air because it causes less interferences, because the drones that we want to detect will also fly a little bit high. And so we first try to find the high points on the buildings, and then we try to listen with our equipment to any RF signal, because, for instance, if you have a huge Wi-Fi antenna just near our system, it will cause issues. So we try to determine the best position based on height, but also on any other RF signal that is coming. It could be mobile signals as well as Wi-Fi signals most of the time.
Okay, great. And another question did come through. If you're still in the mood for answering them,
Yeah.
apologies for shooting so many at you, but look, let's get through them. So another one says, is there any limit to RF detection on the amount of drones in a drone swarm scenario? You know, maybe you can talk to your own experiences, or maybe theoretical, but maybe what are those limits?
So there are of course limits. We will not be able to detect all the drones if there are thousands of drones, for instance. But I would say that the physical limit is more for the drone swarms than for our system. So if you have thousands or 2,000 of drones, for instance, you will not be able to communicate with them in real time. You will not be able to get a real-time live video of all of them at the same time in the same frequency band, because it's just physically not possible. So of course, this physical limitation will cause physical limitation on our systems, but you will need to reduce anyway the amount of data that you will transmit between all the drones. So this causes us to this poses more difficulty to detect the drones but the difficulties is also on the drone swarm.
Okay, yes, very interesting. Okay, so I think we're almost at the end. I've checked and I haven't seen any new kind of questions coming in. So Antoine, we thank you very much for your presentation and for your time. And for coming back as CERBAIR for a second speaker at GDSN. We really appreciate you talking about these, and I found it very interesting as well. So what we're going to do next is I'll let you say goodbye, and then we're going to take a 10-minute break before we come back to Victor from Parrot showing his next presentation. So Antoine, again, thank you very much for coming.
Thank you. Thank you very much, everyone. Have a good day. Bye.